Today's general interest webinar is entitled Quick Tips for Getting the Most Out of SHARCNet. This webinar will be in 4 separate parts based on topics that come up a lot in terms of tickets and just general discussion that we have with users. So as an agenda, the first topic that we're going to cover is backfilling the SHARCNet scheduler. Now, backfilling is an important property of any high-performance computing cluster in terms of the scheduler and how long it takes to get jobs in. Now, busy clusters like the ones that we have at SHARCNet can have long wait times in the queues, but by understanding what backfilling is, we can see how sort of changing the resource requirements of our jobs might have a better chance of getting in far sooner than we would otherwise expect. So understanding backfilling is a good start on getting good wait times on your jobs. The next thing that we're going to go over is estimating job wait times in the queue. I'd like to prefix this with the art of estimating job wait times. Estimating exact job wait times is impossible in these busy schedulers. But what I'm going to do is I'm going to go over the resources that are available to all of our users on monitoring the queue and getting information that goes towards estimating how long your jobs will be in the queue. Other topics besides the queue and job wait times have to do with files and folders. So a lot of what we do is scheduling jobs, but that also requires files and organizing our data. I'm going to go over an interactive folder file management tool that I use often called sshfs, and then use it interactively with Meld folder and file comparisons. I'll just go over a demonstration of that. The last topic is flexible folder file archiving with DAR. And this is basically an alternative to using DAR to create file archives. This is important if you're doing work that produces a lot of data files and you want to be able to compress them down or archive them into a file archive without losing the flexibility of being able to access some of them or doing differential archives. So backfilling the schedule at SHARCNet, this is an important issue in terms of understanding what the wait times end up being in your jobs and how you can change the properties of the requests of a job so that you might be able to get your jobs to start more quickly otherwise. So really backfilling as described is when the scheduler will run a job that can finish before the top priority job is set to begin. That's the general description of backfilling. So to understand this, we kind of have a bit of a Tetris demonstration. You can think of the scheduler as constantly playing this game of Tetris where these objects are coming in and it's trying to stack them and leaving the fewest gaps possible. So what we have here is a rectangular cube that represents, let's say, one compute node. Along the x-axis, we have CPUs, in this case 16 cores, and then along the z-axis, we have memory. So these cores share a certain amount of memory, in this case 36 gigs. And then up the y-axis is time. So over time, these jobs come in, jobs will take up a certain amount of time, and then the scheduling cycle will move up a long time as time passes. So here we see the scheduling cycle. Now, this is the context for which jobs happen at SHARCNet. We have a certain number of CPUs. First of all, we have a certain number of cores, or a certain number of nodes. Each node has a certain number of cores. They share a certain amount of memory, and then they keep processing over time constantly. And what we do is we submit jobs. At SHARCNet, we submit them using sqsub. We name a queue, in this case MPI, and if it's MPI, the number of cores, and then the number of the amount of memory per process, and then the runtime. So let's just visualize what this job looks like, an MPI job with 8 processes and 2 gigs per process for 3 hours. So that, in this demonstration, will look something like this, where we have 8 cores along the X, and then these red bits represent 2 gigs of memory for each block. So each process has 2 gigs of memory. and then the 3 hours is on the y-axis. So the scheduler gets this and it dumps it in, and this job can start running right away. Now, eventually, what happens after? We get another job. So a threaded job, n of 6, and the memory process is 12, so this would be 12 gigs altogether, shared among the processes for 2 hours. This threaded job would look like this, where the memory is shared across the cores, and it runs for 2 hours. Again, there's enough resources available, and this job can start right away. So we have another job, because now this time it's a serial job with 8 gigs for 1 hour, and that would look something like this. So we have 8 gigs of memory on 1 core for 1 hour, and that job is able to start right away. So the next thing that we see is that there's still 1 core left, but all of the memory is taken up on this node. So this core will remain idle because there's no more memory available for a job to run. There's no job that could possibly be small enough to operate with no memory. And then we see that everything's full, so the scheduler moves on to the next time, and it's going to check to see if there are any jobs that it can run now. So at this time, most of the memory is taken up. There are still 8 gigs of memory available in 2 cores. Available here. So if this job is now priority on the queue, where it's a threaded job with 2 processes, and the memory per process, or 2 cores in 1 process, and the memory is 4 gigs with a runtime of 12 hours, which will look like this, we can see that this job can actually start with the resources that are here, and then it will continue to run for 12 hours, something like that. So this is fine, everything is good. The node is relatively full. There was 1 idle core there at the beginning, but otherwise it's pretty full. So really, the space that this job takes up is the amount of memory that was used for the amount of time, and then the number of cores. So I'm just going to reduce this down to 2 dimensions and show it along the back wall so that we can see exactly what's going on as more jobs come into the queue. So the scheduler is moving forward, and then there's another job in the queue, MPI, 16 cores, and the memory per proc is 1 gig. That would look something like this. 16 cores across for 1 hour, and it requires 16 gigs. Now, the first place where this is available is at the end of this 12-hour job, which is currently running. Because it needs all the cores, this is the earliest that this top priority job can run. This 12-hour job that's currently running is defining when this high priority job can run based on the time estimates that were given by the job. If the job actually finishes earlier, and let's say the scheduler gets here, that job finishes, the high priority job will have the opportunity to work here. Now this is one of the reasons why it's impossible to actually say or predict the start time of jobs, because the scheduler is working entirely based on the estimates that are given by SQSub. Now, in this case, we'll see that that job will change its start time, and it will decrease the time that's available in here. Now, let's just keep it at that. Let's say this job does keep running for the 12 hours, and then more jobs start coming in. So let's say a serial job with 34 gigs for 18 hours. That would look something like this. 18 hours long, takes up 1 core on the x-axis, and is requesting 34 gigs, which is pretty much all of the memory on the node. Now, the first place that this could actually happen is really after that 16-core high priority job. Now, let's say we know it doesn't actually take 18 hours, and we could try and run it in 10, reduce its time. Then what can happen is, given that this threaded job is only 2 gigs, and there's a 16 gig job that's still currently running, our new one can't start. There's not enough memory for it to start right away. But on the next scheduling cycle, it could start here and run for this period. Now, if this is the case where we have a 34 gig serial job running simultaneously with the 2 gig threaded, that means that the rest of the node for this entire duration will be idle. That is, although there are all of these cores available for all of this time, there's no memory available on this 36 gig memory node. So these will remain idle for that duration. Now, let's say we know something else, that the memory consumption of jobs isn't constant over the time. And let's say in an extreme case, we find out that this job that we submitted for 10 hours and 34 gigs only required the 34 gigs at the very end of the job, but otherwise was just using a couple of gigs of memory. Now, in this case, it would be much better to separate the job. Now, there are a few cases in which separating jobs is beneficial. If the memory is constant for a job over the run of it, it's not necessarily beneficial to separate it up into smaller chunks and submit it as separate jobs to see if they'll fit into the scheduler better. But if there are big memory differences, then it is certainly beneficial. Now, in this case, this green arrow represents a job dependency. So I'll scratch that out, get that one out. And then what we'll do is we'll submit a serial job that only needs 2 gigs for 9 hours. That's this job. And then that one can start running right away because it only requires the 2 gigs. And let's say that gets named job 123. Then we submit a second job with the W flag. So wait for the completion of this job, and then that one will start. And then that gets flagged like this, a green arrow where this 36 gig job can then start. And then the only place where this node will be idle is during that time. Now, this is the sort of thing that we want to have happen. Now, the other thing that's important here is that the scheduler ends up being very full of jobs, and having requested all 10 hours at 34 gigs would make it very difficult to fit in anywhere. So isolating this to the 1 hour would certainly allow these jobs to happen much sooner. Now, another important thing to mention here is, although we're talking about these jobs as though they're coming in sequentially, the actual order of these jobs, the ones that the scheduling cycle is trying to put in, are ordered by priority, which isn't the same as chronologically. So users change in terms of their priority and within their groups quite a bit, and this is an important property to figure out. Now, whenever you submit a job with the W, it's important to note that even though this job can't start right away, and it may not be able to start for a long time, it stays in the priority with its prior job. So you aren't punished for separating your job in that way. So let's say some more jobs come in. An MPI job with 4 gigs, 9 hours, scheduler moves up, that can start right away. A threaded job, and then 4 gigs with 6 cores, 3 hours, you can start right away. Another 12 gig job, starts right away. And now let's say we want to submit an MPI job with 6 cores and 6 gigs per process for 5 hours. Now the first place that this one can start is up here. There's nowhere for this cube to fit down within here, and this 16-core job is the one with the highest priority waiting to get in. Okay, so we cannot do anything to move that job up. So let's say this job actually looks like this, where it uses up, each process uses up a little bit of memory that has a memory spike at the beginning and the end. Now, what we can do is, if it is the case that this is an MPI job, but it doesn't really benefit that much from running in parallel, that is, it's not sharing all that much information, it's actually better to submit these as separate serial jobs, assuming that these are in somewhat of an embarrassingly parallel state. Now, if it is a consequence in performance that these jobs get separated, and that's not recommended. So what would happen is if we separate this, rather than having to put in one block, we would actually submit 6 serial jobs, and then maybe they could fit in like this if we were recommending the full 4 gigs per job. Now, if we look at the memory involved, during this time, too much memory would be requested. So these jobs can't actually run at that time, or these, because there would be a period of time requiring too much memory. And then the same thing up here, where this period of time, these cores need to be idle because all the memory is being used. Now, we could start 2 jobs there, and then the rest of them would have to start later. So the total end of this would be at the same time as submitting it all at once. But then what if we also submitted dependent jobs where each of those serial jobs was separated based on its memory? That is, this 4 gig part was submitted as a 1-hour serial, and then this 3-hour one was submitted dependent on that one, and then further make the last ones dependent. Now, this assumes, of course, that this is an embarrassingly parallel process, that there are major differences in the memory at different times in those serial jobs. But if we do this, we can see that now this big complex job can actually backfill a relatively complex environment that's in the scheduler right now. For example, 6 serial jobs could start in here. That is, these 6 start. Then the smaller memory serial jobs could start there, and then on their completions, the ending 4 larger memory jobs could start there, and then those can start there. So in this case, by separating the jobs into smaller portions with very specific resource requests on each one, this larger job, in terms of being separated into its smaller parts and separate jobs, is able to backfill a complex scheduled environment that has all kinds of memory constraints and time constraints. All of those now fit before the top priority job is set to begin. And that's really the definition of backfilling. So now, given what we know about backfilling based on this Tetris example, we can talk about, once you have jobs on the scheduler, what tools do we have in order to estimate how long they're going to be in the queue? Okay. And that's what I'll go over next. Now, it is important to note that there is no way of knowing for sure when a job that is currently scheduled is going to start. Now, we have resources at SHARCNet in facilities and performance, and if you go to current, we can look at some properties of the major systems. I'm currently working on Orca, and Orca is one of the ones that's the most demanding. It has a very complex scheduled environment because there are so many resources there and there are so many users. The other thing that really affects this is the number of allocation projects that are in there that have high priority. So importantly, you can go to this page and you can see that there are actually idle cores on the system, and you can scroll down, you can get an idea of what kind of wait times, and these are sort of broadly statistical, what kind of wait times exist on those systems. But all of these are very misleading. Now, the main thing is, whenever you see idle cores on a system, remember that these can be idle because there's no more memory left on the system. Now, during the backfilling demonstration, we showed how an entire node can end up being idle for very long periods of time because a few jobs are taking up all of the memory. Now, if your jobs are in this state where they're taking up far more than their core's worth of memory, it would be important to look at other options. Look at larger memory systems, for example. If you're currently taking up a lot of memory on Orca, it might be very valuable to move over to a system like Redfin. And of course, the estimate of your memory should be very accurate. the scheduler isn't working based on what is actually being consumed, but is always working on scheduling jobs based on the estimates that were given. Now, you can find some basic statistics on wait times based on job properties, but this always has to be taken with a grain of salt. The wait time statistics are based on all kinds of misleading information. For example, if users are doing massive serial farms where they're submitting thousands and thousands of jobs, which can be done and is a valuable thing to do on these systems, the throughput of those jobs, all of those jobs will never start running immediately. Their priority will keep getting manipulated, so they have sort of a constant throughput. But jobs that they submit initially will have very long wait times within sort of a massive serial farm. Now, the wait times of those final jobs really have nothing to do with submitting a single job and expecting and trying to estimate what its wait time is going to be. Another thing is that users are submitting jobs dependently queued. If you submit a job for 7 days and then submit another job that's dependent on that job's termination, then you are naturally forcing that second job to have a 7-day wait in the queue at best. So all of these jobs that have very predictable long wait times are being used in these general statistics. And then in terms of estimates of idle cores, there are also all kinds of other properties going into that are misleading. So really, whenever we go into the queue and we want to get estimates of how these jobs are going to run, the best way to do it is to sort of get involved in what is actually in the queue. So typically, we log into a system. In this case, I'm in Orca, and I'm logged in as a Certification 1 user, and I'll do something like SQ jobs. So SQ jobs returns what it knows as my jobs, and in large queue systems, these things can take a while to respond. So I have a bunch of done jobs in here. The other thing that I can use SQ jobs for, though, is to summarize what is currently going on in the queue. So if I use the N flag to SQ jobs, we basically just get a little summary of the number of cores, how many are busy, the number of jobs suspended, and then how many are queued. And if I use S, we get a rundown of the jobs that are actually on the system in the queue, how many jobs are in which state, et cetera, et cetera, et cetera. Now, on Orca, we typically see a large amount of activity in here. Now, to see the whole thing, and this is typically what I do whenever I'm monitoring the queues, to see if there are any jobs in there that have unusually long wait times or there might be a problem with them, I do something like SQ jobs, A for show all the jobs and show all the queued jobs. Now, being logged in as a Certification Level 1 user, we can still see all of the jobs on the queue. Now, you can see these jobs are many, many jobs. These are all the queued jobs, not the running jobs. We can get an idea of what queue they're in. So we always see on Orca a lot of these NAP jobs for the allocated jobs that are going to be very high priority. And we can also see the time that they have been in this state. So up to 144 hours, and then we see that there are jobs that have been in the queue for over a week. Now, a lot of these jobs are in this state for good reason. These jobs we see here, it doesn't list the end of them. There are 44 more in this sequence because this is part of a large farm of jobs. Now, one thing to do while you're in here is, if you're intending on running, you can look at these queues and explore them, but really get an idea of if there are any jobs that are similar to ones you're planning on submitting. So one thing that we can do is we can say that we want to show all the queued jobs, but let's just look at the MPI jobs if that's what I'm planning on running. So what this will do is it'll reduce it down so that we don't have to look at all of those back jobs, but we can see that there are jobs queued with 8 processes MPI, and they've been in this state for 14 days. Now, of course, being in there for 14 days is also part of the fact that this was part of a farm of jobs that is currently progressing through its run. Now, moving down, we can see some more. There are these 8 ones for 24 hours. And this is also part of a farm. There are another 121 of these jobs. Now, from here, as a user, we can actually go down and we can look into properties of those jobs. For example, if we wanted to know maybe why one of these has been in here for 65 hours, we can do SQ jobs L, its properties, and then get some of its properties. We can also use qstat-f and get more details about that job, and then we can see more specifics about it. For example, it's requesting 8 processors on 2 nodes with 4 process per node, and then each one of those is 2 gigs per rank. So then we can use this to get an idea of the likelihood of, if this is similar to the type of job that we want to run, what kind of weights we can expect at the time. Now, one thing that sqjobs-a show all of the jobs in the queue, and we can also do something like all running. Then we can have a look at what jobs are currently running, and then go farther down into each of those jobs to see how long it was in the wait, using things like sqjobs-l or qstat-f. Now, one thing that we don't see with sqjobs-a whenever we're trying to list all of the queues is the actual priority. Now, this is sqjobs-a returns a chronological view, but if we use something like show queue I, this lists it in terms of the priority. So we'll let this go, and then we can see that there are all kinds of jobs in this queue. Now, importantly, if we look here at the very end, the order of these are not chronological. This will show us the actual list of jobs that are in the queue based on the priority that they have, where the top of this list is the top priority jobs. And what we'll see is that as we get higher, we'll start to see more and more of the NAP allocation jobs. So importantly, in a system like Orca, there are many, many allocations that are running at very high priority. And this is one of the reasons why, given the properties of your jobs, it may be valuable to move over to another one. Now, another thing is, if you aren't getting the sort of allocation that you need in the general fair share use at SHARCNet, it may be time for you to apply for a national allocation project. In this case, you'll be upping your priority in the queue and end up higher in this position. Now, there are a couple other things in terms of looking at your own jobs. Let's say now that we actually submit one of our own jobs, so SQ sub, and we'll send it to the queue, MPI N8, proc, 2 gigs. The output file will be output text. We'll specify a runtime of 7 days and tell it to run, what was it? It's a simple little program here. So once this is in, we can get execute jobs. And then there's another function that we can use called show start for a job that's currently in the queue. Now, what I'm actually going to do is I'm going to specify a timeout of 900 and just let this run. So in the really busy queues like Orca, a lot of the jobs that can give you information about predicting your wait times have to go through the entire queue and examine properties of it. In the busy queue like Orca, this can take quite a while. So the timeout flag to these is important, otherwise it'll just time out by default after 30 seconds. Now, what the show start will do is it will give you an estimate of what it thinks is this job's start time. Now, it's important again to realize that these have pretty severe limitations in some cases. It can never predict higher priority jobs coming into the queue in the future, which can happen very frequently at a large scale on systems like Orca that are heavily allocated. So there is no way for it to know that. There are other things that it can't know. It can't understand jobs that terminate prior to their resource request, thus changing the queue. And typically, whenever you use something like show start, it will return something that looks better than what actually happens, particularly on a heavily allocated system. Now, there are other things to do with show start. Now, if this one doesn't return in a couple of minutes, I'll cancel it. But let's say we submitted this job with far more resources than we needed. Now, that will really extend the wait time in the queue. And what it returns is basically an estimate that it will start in this amount of time and then give you the completion time based on its expected runtime. Now, what you can do is, I've just canceled that for the delay, is you can actually put in other estimates here. So, and by that I mean what you can do is you can say, I have this job in the queue and it's taking a long time. What would happen if I were to actually change it? So say that it'll still run on 8 cores, but cap it to running for only 1 day in terms of seconds, which would look something like this. Now, in this case, it will give you an estimate of that exact job in the current queue status, but actually changing the properties to see if that would have a significant effect on when it's estimating the jobs will happen. Now, again, we can't overemphasize that this is really an art in terms of trying to get an idea of how busy the queue is, how much high priority work is being done on it, and then how much the parameters that you're giving in terms of estimates have an effect on those jobs. Now, if we let this run for a while, it would give us an estimate of this current job, not with the resources that it was submitted with in terms of 7 days, but now a new resource request of 1 day. Now, in the interest of time, what I'm going to do is I'm going to cancel this. Now, there are some other interesting functions like show BF, which tries to show backfilling information of what resources are currently available to run. But all of these have sort of misleading traits in that they might not consider memory in a realistic way. It might say there are all kinds of resources currently available, but that's not considering that all of the memory on those resources are currently being allocated. So always be careful when looking at different things. Really the best way to estimate start times is by understanding in sort of a total way what's happening in the queue right now in terms of priorities and resources that are being requested. Now, moving on from the queue, I'm going to go into some file management resources. So we do a lot of work, and the hope is that we spend most of our time on SHARCNet, just allowing SHARCNet to process and generate throughput in terms of compute time. Now, we also spend a lot of time managing files. So this is what I'm going to go through next. In terms of resources to make it as intuitive as possible to be managing files on your local workstation and then in your work directory, and then even moving from your work directory over to something like Freezer, which is more of a long-term storage type thing. So what I'm going to do here is I'm currently in my local computer, and I have these projects, and I have a few folders, one called My Study. I have another study folder called My Study R for Remote Freezer, and then Remote Work. Now let me just open a browser and we can take a look at this. So I'm currently in my projects study, which has a whole bunch of things in it, and then we also have this empty folder called Remote Work. Now, what I want to do with sshfs, the program, is actually mount the folder in my work directory at SHARCNet so that I can see it locally and interact with it here. And the way that we do that is pretty straightforward. So what we do is we say sshfs, and then we define the folder that we want to mount. So jdejard at dtn.sharcnet.ca. Now notice I'm using dtn here. dtn is very valuable in this way, not the least of which it sees the most files, the most folder paths on SHARCNet, including many of the system scratch folders, and it sees the internet. It's also a very good sort of one-stop shop. If you're going to optimize any one address with your institution for fast research access, you should make it dtn.sharcnet.ca. And then I'm going to go into my work, jdejard, and then what is it called? SHARCNet General Interest Webinar. Quick tips. So basically, in my work directory, under a folder for this presentation, I have a matching folder from my local folder with projects in My Study. Now what I want to do is I want to mount that directory to the one that I have here called My Study. Remote Work. Okay. So what's happened now is if I go back to my file system, I can see that in My Study I have this, and there. So now we see that My Study, that is the local one that has all of my files, is now matched inside of my R or My Study Remote Work. So here we have all the folders that are over on in my work directory. So what I can do is I can now open up this little thing and just edit a file. So natively from my file browser, and say just adding some comments, basically just editing a file meaninglessly. Save it. Okay. So what I've just done is I've through my local file browser, after mounting it with sshfs, just opened a file natively in gedit, edited it, and that edited the file that's over there, SHARCNet. Now what I can do is to sort of get an idea of how these match and show the difference, I can use Meld from here and show the difference between my local study, which is called My Study, and then the folder that I've mounted to the work. So my study remote work. And what this will do is it'll bring up a folder comparison where on the left I have my study, on the right I have my study at work, and it will default to highlighting any differences between the two regions. If I double click on a file, we can see that the one that was remote, I had just edited it. Now, to make the changes, I could just click on this, which will add the text to my local version, or I can just click on this and then copy left, like such. And now the two systems are equal. Now, going beyond this, you can do actual multiple comparisons. You can add a third comparison. So in this case, what I could do is, although I do most of my work at the work file system on SHARCNet, we don't want to leave files there and accumulate them there for long periods of time, trying to keep that system as efficient as possible. So often, if we want to keep files up in the SHARCNet file system, we can move them over to the freezer system. So we could actually also mount the freezer folder equivalent. In this case, if I reduce these, you can see that we could also mount this one and show all three of them side by side. Now, in the case we're using sshfs to mount two remote folders and then using Meld to transfer between them, you need to know that it's very inefficient, as it will actually be bringing the data down to your local computer and then sending them back up to the other. So this will be a huge inefficiency in terms of transferring files between two remote directories, although it's extremely valuable in terms of visualizing what you have backed up in your freezer system versus your work system. Now, in terms of actually archiving data from your work directory over to something like the freezer system, there's a resource called DAR that's valuable for this sort of thing, and that's what we're going to go over next. So, another thing that can happen that can affect the productivity of not only your own use, but of all users on SHARCNet, is if there are massive accumulations of files. Now, it's recommended, and this comes up in tickets very often, of how to deal with having too many files. And we've implemented a quota of, if you have 1 million files, basically new jobs won't start. Now, one of the ways of dealing with this is by creating file archives, where if you have a process that's creating lots and lots of files, you can then just take those files and create an archive. Now, typically the feeling of creating an archive is those files then become hard to interact with or recover, as they're all inside of one file, although it drastically can decrease your file count. So what I'm going to go over is just a quick demonstration of a more flexible sort of archiving procedure, and that's the use of DAR. So here I'm in a demonstration file in my home directory, and it's my study, and then if I list what's in here, you can see that I have input folder, an output folder, and then a stuff folder, and then I have several files inside of each of these folders. Now, what I want to be able to do is take this and create an archive of this entire folder structure. And the way that I do that is I do dar flag C for create, and I'm going to create an archive in my freezer file system, and I'm going to call it dar, and I'm going to call it my study. Now, the thing that I'm going to put into that archive is G for go to this specific thing, my study. Okay. So what this will do is it will take my folder, my study that I have these separate folders and data files in, and it will put an archive over in my freezer directory in a file called dar my study. Okay. Now, it created this dar archive, and one of the important differences between something like dar and tar is that the contents of a dar are easily accessible without taking very long. You can look at basically the content list of the file without having to extract everything. So one of the things that we can do right away is we can use dar then to list the contents of this thing that's over in my directory. So we just need the name of the archive, and then what this will do is it will list everything in it at the time that it was saved. Now, being able to see everything in it is one thing, and then what we want to be able to do is actually, assume that we're going to keep working. We've created this archive, a full archive of my study folder, but really we're going to continue working, and we might have, we might now purge files out of there, and we're going to keep working. So what happens then is if I go into CD my study, and then let's say add some inputs. So this is in what are those called? In file. Let's call it in file 8 or something. So let's say I've just added another input file. What I can do now is, as this is a large scale, I don't have to create an entirely new archive, a full archive. What we can do is create differential archives. So the way to create a differential archive is then by going back to where I was, doing the exact same thing that I did earlier, where I'm going to create an archive. In this case, I'll call it dar d1 underscore my study. But then, importantly, what I'm going to do is I'm actually, instead of specifying what folder I'm going to create the archive of, I'm going to specify the previous archive that this will be based on. So that will be the current full one, which is in freezer, JDaJard, and then it is called dar. Unfortunately, this is still showing up. Excuse me. Okay. So what this will do now is it will create an archive, but it's not going to create a full archive again. It's now just created a differential archive. And then we can go up and just list the contents of the differential archive. And then see that although it knows of everything that is in the full archive, we see that it has only included a couple of saved differences. That is the folder the new input file is in, as well as the new file. And then we can keep creating these differential archives and building it up, and then only occasionally building a full set of archives. Now, another thing that dar is very good at is extracting only the specific files of interest. For example, if I had deleted all of my output files, we could then use the -x flag to extract files from the dar, and then the -g, so go into that directory and extract only the files that I was interested in. So there's no need for extracting an entire archive in this case. You can very efficiently just grab the things that you intend or wanted in terms of files or folders. Really, and that's it for the demonstration for dar, and that's all that I intend to cover today. So I think at this point we can open it up for questions. But anything, again, anytime you want other questions, you can contact help@sharcnet.ca or submit a ticket. The other thing is many of these topics there are many tickets for. So doing a search on the portal will often return good discussions about issues like queue wait times and resource requests in the scheduler, as well as file management. Okay. So thanks a lot.